Now we're going to look at the three possibilities of two lines that may be intersecting. And these are the possibilities. The lines could intersect at a point. They could not intersect because they're parallel. And those two possibilities occur both in three-dimensional space and in two-dimensional space. But three-dimensional space has this other condition that the lines do not intersect because they are skew. The skew lines are not parallel, but they do not lie in the same plane. And this figure illustrates that. You can see the line CD lies in this plane, while the line AB lies in a plane that's orthogonal to it. So there's no way you could have a plane that would include both a plane that's perpendicular to another plane. So these skew lines are not in the same plane, and they're, like I say, they don't occur in two dimensions, but they occur in three-dimensional space. Let's go back now and look at our three possibilities. Now we have they're intersecting at a point, or they're parallel, or they're skew. We're going to start with the case of parallel lines. The reason we're starting with parallel lines is because we'd like to eliminate this first. The procedure for determining if the lines are skew or intersecting is involved, and it'd be nice to just eliminate this possibility, especially since it's fairly easy to do. So we need to recall how we write the equation for the line. In general, it was RT equals R naught plus TV, and R and R naught are position vectors, and all these notes, when I write with this pen and tablet, I'm not marking vectors versus scalars because I have enough trouble writing with the pen as it is. Maybe someday I'll figure that out, or use some different kind of instrument here. So we have two position vectors, and then we have the vector v. T is a scalar. And the vector v we placed, for convenience, along the line. So if we say the vector v is parallel to the line, remember it was a general vector. We treated it as a general vector and we moved it. Well, if you move vectors, they maintain their identity as long as they keep the same length in the same direction. That means they'd have to point in the same direction, and therefore, that's how we're moving them. So another line that's moved, another vector that's moved onto the line would also have to be parallel to v. And that's the whole idea here. We're going to see that the first line includes some vector v, and the second line we're going to look at its vector, but we're going to look at it through the direction numbers. If you remember the lecture on the symmetric equation, the vector v was written in terms of its components were ai, bj, and ck. Of course, we don't have to rederive it. All we have to do is read it off from the equation for the line. So here are the components of v sitting right here because they're multiplied by t. So we have the ABCs for the first line, 4, 2, 4 in this case. For the second case, well, there's a 1 here and a 2. So here we have the direction numbers for L2. Now, if the direction numbers for the first line and for the second line are scalar multiples of each other, then the lines are parallel, because that just means they're in the same direction, just longer or shorter, right? And we see here that they are, in this case, the scalar is 2. It could even be a negative number. It doesn't matter if the vector is pointing one direction or the other, as long as the numbers are scalar multiples of each other, the direction numbers. So having eliminated those, now we can go into the procedure for the skew lines and the intersecting lines. So this procedure involves an overdetermined system of equations. So in this case, we've eliminated the fact that they're parallel, so we have lines that are not parallel. And what we do here, here's the procedure. We're going to write again the equation, the the vector equation, the parametric equation for each line. But we're going to write the first one using t as a parameter like we always do, and the second one we'll write with s as a parameter. Of course, you could use any other letter, just use two different letters. And now what we have here is this is x, and this is the y, and this is the z for along the line. Now if these lines intersect, which we're going to assume they do, and then try to eliminate the that they don't when they're skew, and then find the exact point of intersection if they do intersect. The x here, this x value from R1 has to equal the x value in R2. So we equate those. That gives us one equation in our system. The same holds for the y's. So here we have the y from R1 has to equal the y in R2, and we write that as the second equation in our system of equations. And then, of course, we're going to have, obviously, the third one. And this is for the z's. Okay, this is an overdetermined system because we're looking for values of t and s that will give us the same x, y, z in both line 1 and line 2. So we have two parameters we're looking for, t and s, and we have three equations. That's why this is an overdetermined system. In order to solve this, what we do is pick two of these equations, the ones I'll do right now, pick the one for x and the one for y. From this, we find values for t and a value for s that works, assuming that the x's match and the y's match. Then we take these values and put it in the remaining equation. If we get an equality, then they intersect. If the result they're not equal, then the lines are skew. So again, the procedure is to write these three equations as a system, pick two of them. I'm picking the ones for x and the ones for y, but it might be a different choice, might make it easier. Solve for the values for the parameters t and s, then put those back into the third equation and see if you get equality, or if they give equality rather. We'll show how this works with some examples. So this will be an example of a skew lines. So we have R1, again written with the using t as a parameter, and here R2 is written with s. Then we equate, example, the x's, and put that as the first equation. Then we have the second equation and the third equation. And now we're going to take the two equations here and solve them. Here we've rewritten the first two equations. This is the equation for the x components, and this is the equation for the y components. And we've written, it's a 2x2 system, easy to solve it by observation would work, or elimination, substitution, whatever you want. And the result ended up being t equal 1, s equal 1. So that was a solution. We do get a solution here. I'd like to make a kind of a remark. Later in this class, we'll be looking for collision points. Now, if t is treated as time and two lines, not necessarily intersecting straight lines, they could be curves, if they cross at the same time, then the point is a collision point. And so in those cases, you're looking that t and s have the same value at the same locations. That's not the case here. These just turned out to both have the value 1 by accident, I guess you could say, and it wasn't required for this case. Well, what happens now is that we take these values of s and t and we put it in the remaining equation. Here was the remaining equation. This is the one for z. And when you put 1 in here, you get, of course, these aren't equal. Right, because the lines are skew. Right, so that's the procedure. We're going to do the same procedure again for the case where lines intersect. We'll use the same R1, but we use a different R2 in the next example. So again, we have the same R1, but R2 is now different than it was for the skew line. We take just the same procedure as before, just repeat it a little bit so that you got that firmly in mind. There we go, equating the X components here, equating the Y components here, and equating the Z components here. And here's our overdetermined system. So as before, I'm going to take these two equations and solve for values of S and T. And here are those two equations. This is the one for X, and here's the one for Y. And we solve, we end up with the same numbers, but that was just possibly an unfortunate accident. We end up with both of them equal to 1 again. Now these are different lines, so we're going to have a different result. Here is our remaining equation, the one for Z, and we substitute in T equal 1 in this case, and we substitute again S equal 1 here. And what do we get? We get 1 equals 1. We get equality. And because we get equality, that tells us that these lines do intersect. And they intersect at a point, and we'd like to find the coordinates for that point. To find the coordinates for that point, remember T was and S were both 1. You go back to the original equation and you find the X, Y, and Z for R1 or the X, Y, and Z for R2. In this case, I've got here, these are the X, Y, and Z for the first line. And I substitute T equal 1 into that equation, and I get 5, 3, 1 for the X, Y, and Z coordinates. That's the point where the lines intersect. I could just as well have used the X, Y, and Z for the second equation, in which case I would have used S equal 1, which doesn't make a lot of sense here because they're both the same, so it's kind of doesn't give a good contrasting example, but we would have had the same point. So again, to summarize, the lines can intersect at a point, or they cannot intersect because they're parallel, or not intersect because they are skew. This is the easiest one to figure out, and you should do that to eliminate, just eliminate that right off the bat. So if the lines are not parallel, then use the same procedure for the intersection or the skew. The difference is when you get to the end and you check the remaining equation, so for that extra equation, you get equality. And for skew lines, it is not equal. And if there is equality, then you have values for S and a value for T. You can substitute those back into the equations, either R1 or R2, and find the point, the coordinates of the point, the X, Y, Z for the point at which the lines intersect.